Good day, folks. This is tutorial number 37, and I want to use the dynamic scenario in 3D Experience in order to solve a common and simple problem that appears in most of the mechanics courses. Here's the situation. Suppose I have a, a plate, a flat plate, let's say made out of steel, for example, and it's pinned at the bearings and released from the horizontal position, allowed to uh, rotate about the hinge and move down. What we want to know is what is the acceleration, initial acceleration of the plate when it starts moving. I will do this problem for you, and then I will come back and repeat it where instead of a rectangular plate, we have a triangular plate. Now, let me first say a few words about the rectangular one. It's made out of two parts, a bearing and a plate, like that. And the dimensions are given by the dimensions of this plate are 2 meter by 1 meter by 4 centimeter thickness. And I'm assuming that it's made out of some material, and the mass of that plate is 160 kilogram. Since I'm going to be modeling this thing from scratch, let me assume that these extensions are 20 centimeters long, and the radius of that shaft, the radius of that cross section, is 2 centimeters. Okay, now uh, here is the same information, but written as the thickness of this. The thickness of this is 4 centimeter, right? Correct. Now, this can be done analytically. That's why it appears in most dynamics textbooks. So if I ignore the ends of this plate, then we have basically a block, and the mass moment of inertia about the y-axis can be found by the parallel axis theorem to be, based on the information that's given, 53.33 kilogram meter squared. And because we know that the mass moment of inertia about that axis, axis y, times the angular acceleration about the axis y is equal to the moment applied, and the moment is actually coming from, moment about y is coming from the weight of this rectangular plate, which is concentrated at centroid, times half of h. Okay, so mg is the weight of the plate times the moment arm, which is h over 2, half of this width. It comes out to be 14.714 rad per second squared. Now, when I do this thing with 3D Experience, notice that the initial acceleration, angular acceleration, is roughly, the figure shows that it's around 15, actually 14.7, which is very close to what we got. And I'm going to repeat this thing. The only difference that's going to happen is that the moment arm, of course, the mass moment of inertia will change. And I took this thing out of a dynamic book, and the moment arm is going to change. Instead of h over 2, is h over 3, and I should be getting 19.62, roughly like that, rad per second squared, and see that. Okay, let's go ahead and do it. So here is 3D experience. Let me start with an assembly. I am already in the assembly design. So I'm going to insert my first 3D part. You can do it from here, right click if you want. Just 1 second. Insert a 3D part. You can do it from here, or you can go to the product modification tab and you do it from there. It's up to you. Okay, so it's going to create a 3D part. I'm going to call this thing the plate. Properties, I'll call it the plate. This is the part name, and there's the instance name, plate. And to minimize my work, I'm going to do it in a kind of a, go into the XY plane and I'll sketch a rectangle there. So let's say that I do something like this. Now I'll clean it up in just a minute, but this horizontal dimension is going to be 2 meters. Okay, and the vertical dimension is going to be 1 meter. And I want to make sure actually this is coincident with that line for reasons that you see later on. I'll make this line control that line. We make it coincident. Push it up. Very good. And I want this thing to be symmetrically located with respect to that vertical line. Left line, control right line, control the middle axis. You see now, left line, control the right line, control the middle axis, and I'm going to make it symmetry. Okay, good. So here's the situation: 2 meters long, 1 meter high, and 1 meter high. And on purpose, I made it so that this local the y-axis is actually exactly halfway between left and right. So exit. Very good. And then I'm going to pad it once again symmetrically to make my job easier. Okay, so symmetric, 2 centimeter on each side, and that's exactly what it's going to be because I clicked on this, it's going to be 2 centimeter up, 2 centimeter down, and it's going to be thickness of 4. Now, on that vertical plane, please note that I'm doing this thing to make my job easier when I do the triangular one, okay? So on that vertical plane, I will sketch. Okay, so what I have here is I'll do it like that, a circle, centered at this point, at the origin, radius, try it again, not a circle with the center at this point, and I'm going to dimension this to be 2 centimeters, 2 cm, there we are, exit. And remember, I wanted these to be two, 20 centimeters on each side. So I'm going to pad that circle symmetrically. On each, since I'm doing symmetrically, there's going to be 1 meter here plus 20 centimeter. So 1.2, yep, 1.2 meters. Right there. There we are, you can see that. And then we say, okay. All right. So what you see there is actually this piece. Okay, very good. Now I'm going to insert my bearing. So double click on the top. I'm in assembly design. So insert a 3D part. Okay. Right there. Double click on this. Let me actually rename this thing to be properties. I'll call it bearing. And bearing. Okay. Double click on this. All right, so to make my job easier, on this face, I will sketch. Why don't I project that circle? There we are. Look at it from the front to make things easier when it comes to making the rest of it. And I'll draw a rest of the bearing. So it's going to be something like this. Exit. Why don't think this was nice and symmetric, so let's go back here, make sure it is nice and symmetric. So why don't I make this circle, control that circle, we make it concentric. I'm doing a lot of extra stuff that could have done it if I was more careful. Exit, there we are, and then we pad it. Let me make this thing maybe I don't know, I'll make this thing 0.1, 10 centimeter. Yeah, that's good. There we are. Why don't I change the color of this also? Right click properties, graphics, and then I made it that color. And for the thing on the other side, I'm going to mirror this thing. So let's find the transform. There is the mirror somewhere, mirror with respect to that. So it's going to go on the other side. All right. The moral of the story is that you can create these any way you want. I did it this way because it makes my job easier when I do the second part of the problem. Okay, which is changing this thing to a triangular flat plate. All right, now while I'm at it, I go all the way to the top and apply apply my restraints. So what do we have here? Constraints actually. So under assembly, here we're going to fix the bearing. So we fix the bearing. Bearing is fixed. Okay. And then I make a revolute joint at one of the ends. It really doesn't matter which side. So we go to revolute. Okay, time. The axis of okay. So I'll use this particular template. Axis, plane, plane. So here's the axis. This is the axis of the shaft. This is the axis of the bearing. This is the plane of the shaft. This is the plane of the bearing. And I don't need this last one. I'm going to delete it because I'm not going to control the motion. All right. So that's pretty much done. Pretty much it. So let me save this thing. Good. And now we're going to go to the uh, mechanical systems design. All right. First, we're going to create our mechanism representation. We're going to create it. And then we're going to check to see what we've got. Needless to say, there's going to be a fixed part and there's going to be a revolute joint. Very good. Now let's assign mass properties. So you go all the way to the right. There it is. Weight definition. Unfortunately, it's a misnomer called weight definition. Okay, everything is red because nothing has been assigned. As far as the bearing goes, it really doesn't matter because it's going to be fixed stationary. But when it comes to the plate, you select the plate here. Okay, and first link, it says click this hyperlink to declare a weight on this element. You click on it. Okay. Now let me move this thing on the side. Right now everything is zero. Everything is zero, so I click on this checkbox here. See that, this box? What it does, it assigns properties of, actually default properties of steel, which has this weight on it, okay? But I don't want that, okay? I want to change this thing. I want to change this. So you left double click, and then you can change it to whatever you want. So 160 kilogram, right? And based on that, it's going to change the mass moment of inertia also. Okay, I noticed that this number 54.22 is very close to the number that I've got here. Is close to this number, and the main reason is that this is based on the fact that the ends and that round shaft basically is excluded, ignored. So, but it's close enough. Very good, close enough. And then you click on it, close it right there, close. Okay, and then if you click on the bearing. Again, you have to assign properties to it. Although it's stationary, you have to give it mass. You click on this link, check this box. So it's going to be whatever, 11.186 kilogram. It doesn't matter. I just keep it like that and close it because the bearing is going to be stationary anyways. Now, we are done here. So we're going to go to mechanical system experience. Say okay. Say okay. All right, so first we activate gravity excitation right there. You need to click on that. Default properties, 9.81 in the negative Z direction. Very good. Let me also create a sensor at this point, speed acceleration sensor. You select that point and say OK. All right, good. Pretty much done. Now we're going to do a dynamic scenario. Dynamic scenario. We add the excitation there. Probe. We add the probe there. And then we go and change the time. Instead of 10 seconds, I'll make it 1 second. And then we say, okay, we can make it 2 seconds. This thing is going to go wobble back and forth, etc. But I want to find the acceleration, initial acceleration. So that's good enough. And now we're going to run it. So put the cursor there, right click, your time. And then say force compute and generate result, or you can scroll all the way to the right here and click on that. Either way, it makes no difference. So let me do it from there. You click and just wait. There. Okay, now we're going to look at the results. We are in the results section. Click on the view scenario results and deselect everything. Just show me the angular acceleration of that point that is selected. Remember, I created that probe there. You click on it and look at the plot. And if you want to see the table, you're going to get 14.0 whatever. Very good. So that confirms this result and is closely agreeing with the analytical calculation. Now we want to repeat this problem with minimum work, except that I want this thing to be triangular. So here's what I'm going to do. So what I will do, I will go to that plate, double click on it so that you end up there, and go to the sketch that actually allowed me to create that plate. Double click on sketch. So what I want to do is I want to delete this line, and I want to delete this line, and just connect that point to this point so that the rectangle becomes actually a triangle. Good. Exit. Everything is the same. Now the only thing is that when I go back to that mechanical systems, let me go there. Actually, let me go to the mechanism. What was it called? Mechanical systems design. Now, what I need to do is I have to change the properties of this triangle. So I go back to weights and definition. Now, that fellow, if you click on it, see this? If you click on the plate, this is the information that I put in there. This thing on the side. I want to put this thing in recycle bin. I don't want this. Okay, notice that the slide here says change the shape, delete the assign by sending it to recycle bin. So you put this thing in recycle bin. Now click on it again. Noticing everything is back to 0. Okay, put the properties of default properties and change this number to 80, not 160 because it's half of the mass. So you click on it, you change this thing to 80. Of course, these numbers are also going to change also. Good. So that's what I did. assign 80 kilogram, and then we're going to run. Everything is the same. So close that, close this. All right, now we want to run it. Of course, you have to go to the mechanical system experience. That's easy to do. If you double click on this thing, it'll send you there. It'll send you there, and I don't have to change anything. Let me just go ahead and run it. All right, so it looks like it didn't like that. So what I'm going to do is I'm going to delete this. I have my excitation, gravity is there, the probe is there. So what I'm going to do is I'm going to go back here and make another dynamic scenario. Click on it, send the gravity to the right, send the probe to the right, go change your time, 1, and then say, okay, it didn't like the fact that I was running the original one, and let's try it now. Right click, update, not update, sorry, go to the, where are we? Uh, Scenario, go to scenario, go there, right click, compute. Okay, notice that it bombed out. It bombed out mainly because it says that I don't know what that probe is. So what I'm going to do is I'm going to delete this. I'm going to make another probe. Let's go back here. I'll do another probe, that corner point. Okay, and then say okay. And let's make sure that it is included in my scenario. Yep. And now we're going to run it. Good. Click on the view results. Deselect everything. Angular acceleration magnitude. Plot it. What unit is this? Let me see what is it that I did. Oh, this is angular velocity. Sorry, I want angular acceleration right there. Plot it right there. And if you look at the table, 19.58, something like that. And there is 19.58. All right, folks. So I hope you found this thing useful, and good luck.